So this week we're going to look at smooth unconstrained optimization problems. These are arguably the simplest class of optimization problems that we're going to study in this course, but they're actually much more common than a lot of the more complicated forms that you will see later in the semester. And so it's an important problem class. This problem class is generically written in the following way. So you minimize some optimization variable x, and x is usually a vector, in this case in Rd, and you measure the quality, the goodness of each, or the cost in this case because we're minimizing, of each vector x with an objective function or a cost function. This is f of x over here. It's very important that f of x is a real valued function, so it outputs a real number. If it outputs a vector, then you get into what's called multi-objective optimization problems, where each component of this vector is a objective in the multi-objective optimization problem. And these are much harder because you can't always compare. There's no sort of total ordering on vectors. And so you can't always compare the output of the objective function. And so to keep things simple, we're going to focus on scalar value, objective functions that output scalars. And like the title of the optimization, the title of the slide suggests, we're going to assume that this objective function is smooth. So meaning we can at least take a derivative. And the reason this is so is because the broad class of algorithms that we're going to see here needs this derivative information. They're called first order methods, and therefore they need access to first order information, aka derivative information about the objective function. So before we move into the details of the class of algorithms that we're going to look at today, why don't we take a step back and try to get some context for why this class of algorithms exists, why sort of they look the way they look. So in your calculus class, you should have seen very simple versions of smooth unconstrained optimization problems. Perhaps the argument was a scalar. Heck, you might have even seen very simple versions where the decision variables had some constraints on them, but we won't worry about that until later. But now think back to what was the way that you were taught to solve these problems. Well, if your calculus class was anything like my calculus class, what happened was you took the objective function and you differentiated it, and then you set the gradient to 0 and tried to solve for the values of the optimization variables that made the gradient or that made the derivative 0. This is doable for very simple objective functions, but for almost all the problems that you're going to encounter in statistics or in practice, you are not going to be able to do this. I mean, imagine if the cost function was the cost function, a loss function of, let's say, some horrible neural network. Well, you can certainly take its derivative, but you will not be able to solve for the values of the optimization variables. In this case, it would be the weights of the neural network that you're training that make the gradient of the objective function 0. You're just not going to be able to do this. It's too complicated. And so this class of algorithms that we're going to look at is basically a different way of approaching this problem that is amenable to a computer executing it. The key is a computer is executing it. If you want to actually execute this algorithm, it would take you an eternity. Okay, so what are these algorithms? Well, generally what they do is they start at some initial point, and this is a point that you have to be, the algorithm has to be told. So this is part of the input that the user has to provide. And what it tries to do is it tries to improve on the initial point. It doesn't try to get straight to the minimum, but it tries to reduce the cost or the objective value of this initial point to get a new point. Okay, these points we're going to refer to as iterates. And from this new point, it's going to try and repeat the process. And the result of this algorithm is that you're going to get a series of points, a series of iterates. And the idea is that the cost function, if you look at the cost or the objective of this series of iterates, you're going to see that they're trending downwards. I say trend because not all of these algorithms produce a strictly decreasing or even a monotonically decreasing sequence of objective value. Sometimes the objective value can occasionally increase, but generally it's sort of trending downwards because you're trying to minimize the cost value. Now, the exact way that the algorithm does this is usually by trying to get some local picture of what the cost function looks like around the vicinity of the current iterate. Say it may make a surrogate model that's a surrogate, construct a function that's very similar to the actual objective function in this neighborhood of the current iterate, and then work with this surrogate objective function. Now we'll see that the class of algorithms we're going to see today actually does this. And then what it tries to do is using this surrogate function, it tries to get a new point that has smaller cost value than the old point. So the specific class of methods that we're going to look at today are what are usually known as line search methods. And so what these methods do is, remember, at each iteration, what it's trying to do is trying to get a new point that improves upon, that reduces the cost value, at least improves upon the cost value of the current iterate. And so line search methods sort of do this in two steps. So first, what it does is it starts at the current iterate and it decides on a direction to go. Okay? And this direction is what we're going to denote here as D. Okay? And it's just a vector in RD. Once the direction is picked, it will execute a routine which is called a line search, because you're just sort of searching along the line, searching along this direction for exactly how far you're going to move along this direction, how far the subsequent iterate is going to be in this direction. So you first pick the direction, and then you pick how far you're going to go in this direction. The process of picking a direction, there are many ways to do this. We'll get to a particular way today. The second step of picking how far along this direction you go, this is called a line search, and that's why this class of methods gets their name. Now, what is a good direction? So a good direction is a direction that in some sense points in a direction that you would get some decrease in the cost value. And more formally, what you would like is you would like the directional derivative of the objective function along this direction to be negative. Okay? And if the direction satisfies this condition, namely the directional derivative of the cost function along this direction is negative, then this direction is called a descent direction. It makes sense because along this direction you have the possibility, at least locally, of decreasing the function value. Right? Okay, so yeah, this is what I just said about line search methods. What you generally do is at your current iterate x sub t, let's say, throughout this, probably this whole semester, we're going to use basically t's to index the iterate. So it's not time. So we're going to use xt to index the iterate. So at the current iterate x sub t, you're going to move in the direction d sub t. So that's the search direction at the tth iteration, the direction of movement. And then you're going to move along this direction by an amount eta sub t. That's going to be the step length. Okay, the step length might be different at each time, so we also index this by t. A classic example of a line search method is, so to specify a line search method, really all you need to do is you need to specify how you're going to pick these descent directions, these d sub t's. And the easiest ways to pick it is to just pick the negative gradient direction. Okay? Is to pick the negative gradient direction. And it's not hard to see why this is always a descent direction, because if the function is smooth enough, in particular, if it's differentiable, then the directional derivative is simply along a particular direction, is just the gradient of the function inner product with this direction. Right? Both are vectors in RD, the gradient is a vector in RD, the direction is a vector in RD, and so the directional derivative along this direction is just the inner product. Well, if I pick the direction to be the negative gradient direction, then this inner product is just going to come out to the negative square of the Euclidean norm of the gradient. Right? And this is a non-positive quantity. As long as the gradient is not zero, this is actually a strictly negative quantity. Right? So you're always going to get some descent along this direction. And this is in some sense, and this is why this motivates the choice of the gradient as a descent direction. And if you do this, then what you get is you get this method that we're going to refer to as gradient descent, GD, and this is the method that we're going to study in this class. This is a very old method. Idea, people, historians have traced this back to Cauchy in 1847, but this idea, I don't know, probably goes back maybe even further to the time of Newton. I don't know, but again, the idea here is that you're going to move in the direction of the negative gradient. Now, how much you move, that's unspecified, but as long as you move in the direction of negative gradient, it's a line search method in which the descent directions are chosen to be the negative gradient at the current iterate. Then this is what we're going to call gradient descent. Okay, so this is just some justification for gradient descent. Again, as long as the gradient is non-zero, picking the negative gradient direction as a descent direction guarantees that this directional derivative will be strictly negative. Okay, will be strictly negative. And so as long as you move a little bit in this direction, Taylor's theorem will tell you that you can at least decrease the cost value by a little bit. Okay, and this is the basic motivation behind gradient descent. Okay, so we're going to look at this algorithm in three contexts. So the first is in some sense the simplest context. It's quadratic optimization problems. Later on, we'll look at more general problem classes in which the we're going to start by imposing very strong assumptions on the cost function. We're going to start by assuming the cost function is quadratic. And then we're going to slowly loosen these restrictions. We're going to loosen them to convex, and then eventually we're going to look at non-convex cost functions and how gradient descent sort of performs on those type of problems. Okay, so a quadratic optimization problem is just an optimization problem in which the objective function is a quadratic function or a quadratic form. Each quadratic form is specified by a matrix. This is denoted by A on this slide. And we're going to assume that this matrix is symmetric and positive definite. The positive definiteness part is basically required for this optimization problem to make sense. If you think about it, if I have a matrix A it's not positive definite, meaning that it's got a negative eigenvalue, then there's some questionable things can happen. So if I take the direction of one of the eigenvectors associated to, let's say, one of the negative eigenvalues, and I just go infinitely far out in this direction, then I can drive the value of the objective function to be as small as possible, or as close to negative infinity as possible. And so this doesn't make too much sense for an optimization problem. I mean, you really shouldn't be minimizing objective functions that can take negative infinity. And so we're going to assume that we're going to rule this out by just assuming that this doesn't happen. And this is the assumption that the matrix A is positive definite. Now, you might ask, what happens if A is positive semi-definite? Then won't the objective function still be bounded below? Yes, but if you want to deal with this case, then it doesn't really add too much intuition to everything that we're going to talk about. But it's going to make just some of the math harder, and it's not really that important from an understanding perspective. So we're going to just skip this, and we're going to just straight up assume that A is positive definite. Okay. Now, one thing to note is that the derivative of the objective function I've written out here is just the matrix A times the optimization error. The optimization error is basically the difference between the current point and the optimum. In this case, is x star. Okay. Oh, and the other thing to note is that in the way that I've written the objective function, you can read off what the optimum is. The optimum is just x star, right? Since A is positive definite, the quadratic form is always bigger than or equal to 0, and so if I just pick x to be x star, I get 0, and so this achieves the lower bound, and therefore that is the global minimum of the optimization problem. Okay, so let's look at the convergence of gradient descent on quadratic programs. So just to be concrete, we're going to be looking at a version of gradient descent with constant step sizes. What this means is that this eta t parameter, how far you go along the negative gradient direction, this will be the same for every iteration. Now, this doesn't mean that you are moving the same amount each iteration, because remember, your move, so to speak, is the search direction multiplied by the step size. So even though the step size is constant, the magnitude of the search direction, in this case the negative gradient, can still change from iteration to iteration. So you're not moving by the same amount each iteration. One thing that you'll notice about gradient descent is that it's actually one of the most robust optimization algorithms out there. The general rule of thumb is, as long as you set the step length to be less than some critical threshold, we'll talk about what this critical threshold is later in this video, but as long as you set it below this, you will be fine. And so, meaning the algorithm will converge. It may converge rather slowly, but it will eventually, given enough time, it will sort of eventually get there. So if you have a problem and you're sort of having some trouble solving it with other algorithms, try gradient descent. If it even sort of messes up with gradient descent, then perhaps it's best to go back to the drawing board and rethink about the problem you're trying to solve, maybe reformulate it, because it may be just too hard to solve for a computer. Okay, so that's the business of the step length out of the way. We'll look at versions of gradient descent where the step length varies later on. The other thing is to note that the choice of the step length, right? In this case, it depends on the eigenvalues of the quadratic form. Later on, what we'll see is that the step length more generally depends on the curvature of the objective function. So for a quadratic objective function, the curvature is sort of completely captured by the matrix in the middle of the quadratic form, right? That's the Hessian. And so here, you see that the step length really just depends on the smallest and largest eigenvalues of the Hessian. Later on, you see that it depends on sort of bounds on the curvature, which, if you specialize it to the quadratic case, essentially corresponds to bounds on the eigenvalues or the spectrum of this matrix in the middle of the quadratic form. The next thing to note is that the convergence is very rapid. If you look at what the theorem guarantees you, it guarantees that that the optimization error, so the distance between your iterates, let's say the teeth iterate x sub t, and the actual optimum x star, this thing decreases geometrically in the sense that each time you get to multiply in another factor, and this factor is less than 1. This type of decay is very rapid. It's called linear or geometric convergence. It's called geometric convergence because these are the terms of the geometric series. It's called linear convergence because if you were to plot the logarithm of the optimization error, what you would see is that it's actually a line. The slope of the line is given by the log of this factor that you're sort of multiplying in every iteration. This is not hard to check. Finally, what we want to, the last thing I want to point out is that this factor of how fast this factor that you multiply each time, which controls how fast the sequence converges, it depends on this quantity, which we're going to call kappa of A. And you see this quantity appear a lot, or generalizations appear a lot in the analysis of optimization algorithms. So here we're meeting it for the first time. This quantity is called the condition number. And it is a measure of how pathological, in some sense, the curvature of the objective function is. If you think about what this is, if you look at a quadratic function, so it looks like a bowl, maybe stretched out in certain directions, where there's small curvature, and very narrow in another direction where there's big curvature. The ratio, of the direction of the curvature in the biggest direction to the direction of the curvature, in the direction with the smallest curvature, this ratio is called the condition number. And the bigger this ratio means that the more sort of uneven, the more sort of multi-scale this objective function is. And more multi-scale, more unevenness means that it's generally harder to optimize. And so we'll see analogs of this quantity later on. So the other thing to note is that all the proofs, because proofs have long algebra expressions, they're not amenable to putting in the slides. They are included in the references, so make sure you check those out after you watch the lecture video. Or you can just pause the lecture video here and go read the proof. The proofs are titled in the same way as the slides, so it should be very obvious which proof corresponds to which slide in the lecture video. Okay, so in the preceding slide, what we did was we studied gradient descent with a constant step length. Now this choice of step length seems quite simple, but it suffers from this fact that it's not really practical, because in order to use this choice of step length, you need to know something about the curvature of the, in this case, the quadratic objective function. But generally, you don't know these quantities. You're sort of just given the objective function. In the worst case, what you're given is you're given a sort of a black box oracle, right, where you can give the oracle a point, and the oracle will tell you back, let's say, the function value and maybe the gradient of the objective function at that point. You don't know anything else about this function. It's just sort of handed to you in this type of black box subroutine. Now, if you have this type of setup, then you cannot use this constant step length that we just used to prove the theorem on the previous slide. So what you need is a way to determine how far you're going to go to set the step lengths on the fly. And this is what we alluded to before as a line search routine. And the name is very suggestive. You pick a search direction, in this case, a negative gradient direction, and you're just going to figure out how far you're going to move in this direction on basically along this line. That's why it's called line search. Okay, so in this case, we're going to look at a slightly more practical strategy, but still not very desirable. And what we're going to do is we're going to use what's called an exact line search. So what you're going to do is you're going to exactly optimize along this line. So meaning once I pick the search direction, right, now I'm just deciding where to move along this line, I effectively have a scalar optimization problem where the optimization variable is this step length, how far I'm going to move in this direction. And the scalar optimization problem is generally easier to solve than a big multivariate optimization problem. And so the exact line search just means find the exact minimum of this function, restrict it to the search direction. Okay? And so for quadratic programs, this is possible. In fact, you can get a closed form solution. And so let's see how this version of gradient descent does. Okay, so here's the convergence result for gradient descent with exact line search instead of constant step sizes on quadratic programs. And I want you to pause for a little bit, pause the video, and think a little bit about what this, compare this theorem to, compare this convergence result to the previous convergence result with constant step sizes. So I claim that these two convergence rates are actually roughly the same. Okay, and this may be somewhat of a surprise to a lot of you, because if you think about it, you would expect that this version of gradient descent to converge faster, because after all, you are sort of doing more to reduce the objective value per iteration than in the version with constant step sizes. I mean, after all, the constant step sizes, you're always making the same step size. Here, I am exactly minimizing along the search direction each iteration. Right? Before I was not, so I should be making more progress each time. And the answer is yes, you are going to be making more progress, but in the grand scheme of things, it doesn't really matter. So it doesn't really affect the rate of convergence. You see that the rate of convergence is still linear, and this result is stated slightly differently than before. We stated it so before you saw that the result was stated in terms of how fast the optimization error, so the distance from your current iterate to the optimum, how fast this distance was decaying. Here, what you're seeing is that we're stating in terms of the objective value. Okay. Now, a general rule of thumb is that the objective value is, you should think about it as a surrogate for the square of the optimization error. In this case, because the objective is exactly quadratic, this is basically exactly the square of the optimization error. And so here you see that if I look at the square of the optimization error, this factor in front gains a factor 2 in the exponent, and so but this factor itself is the same, and so really you're looking at the same convergence rate. And this might be very surprising at first glance, but you see that this is quite sort of common. So later on, when we look at different settings of gradient descent, you'll get the same story. And the moral of the story here is that yes, exact line search is better, but it's not much better. There's actually no need to minimize exactly along the search direction. That's sort of the takeaway of the story. So an exact line search, yes, it's more practical than a fixed a priori known step length that depends on all these unknown probable parameters, but it nevertheless is still a little bit wasteful because you're still exactly minimizing each step. And so now you see here that you don't really need to exactly minimize each step. So later on, we'll discuss more practical line search strategies that don't require you to preset a step length based on unknown problem parameters, and also you don't minimize exactly during each iteration. So it's considerably more computationally efficient. Okay, so that was the just a very quick tour of the performance of gradient descent on quadratic problems. So we oftentimes use quadratic problems as kind of toy test cases to check out. Basically, it's sort of like a sanity check for algorithms. I mean, if it doesn't work on quadratic problems, then this algorithm, probably doesn't work in real life. The other reason why we use it as a sanity check is because you see a lot of the properties of the algorithms on quadratic programs actually translate to more general optimization problems. And so now what we're going to do is we're going to relax the assumption. Before we assume that the objective function is quadratic, here we're just going to assume some type of convexity and smoothness assumptions on the objective function. And we'll see that by and large, the convergence results are, maybe not similar, but they're analogous. So the analogous quantity in the general nonlinear case, the analogous quantities to the quantities in the quadratic case, they appear in the same places. And you'll see what I mean once you see the bounds. Okay, so let's look at let's first, pin down the problem class that we're considering. And this is the problem class of strongly convex and strongly smooth optimization problems. Again, we're still unconstrained, so the minimum is over, any decision variable, any optimization variable in RD. The only difference is that instead of assuming that f is quadratic, we're going to assume f is, in this case, twice differential, because actually we don't really need to have it be twice differential, but it just makes things simpler to state the assumptions. And so we're going to assume it's twice differentiable. And the two other assumptions that we're going to stack on are that the eigenvalues of the Hessian, in other words, the minimum and the maximum curvature of the objective function, are bounded between mu, which is a non-negative number, and some upper bound L. Okay. So the lower bound, this is known as what's called strongly convex, so strong convexity assumption. It's just, you should think about convexity. So if mu is 0, then this is basically saying that the objective function is convex. Mu being strictly bigger than 0 means that this objective function is, has some, upward curvature at least, and this is called strong convexity. We'll talk a little bit more about these assumptions later, but for now, in the context of twice differentiable functions, what it means is that the Hessian's eigenvalues are bounded from below by mu. Okay? Now, the squiggly inequality sign just means inequality in the positive definite sense. So if I write a matrix is squiggly inequality bigger than 0, it just means this matrix is positive semi-definite. Okay? Next, for the strongly smooth assumption, it's essentially the complementary assumption. So in strong convexity, you assume that the curvature of the Hessian is bounded from below. Here, what you're going to assume is that the curvature of the Hessian is bounded from above. Okay, and these two constants, mu and L, you see, play the same role as the minimum and largest eigenvalues of the matrix inside the quadratic form in the quadratic case. Oh, and last thing I want to note is that these bounds are sort of uniform. So you have to use the same mu and the same L for any value of the optimization variable, for any x. Okay, so let's look at the performance of gradient descent on strongly smooth and strongly convex problems. And so what we're going to use is, we're going to start simple. We're going to use a constant step length. So this is perhaps not the most practical choice of step length because this, the step length is going to depend on the strong convexity and strong smoothness parameters, mu and L. But what we'll see is that you really get a very, very similar result, almost exactly, the same result as in the quadratic case. And so the only difference is that you have to define condition number slightly differently. So it's still a linear convergence result. The contraction factor still depends on the condition number. It actually depends on the condition number in the exact same way as the contraction coefficient in the quadratic case. You just have to slightly redefine condition number, and the redefinition of condition number is actually very, very, very sort of straightforward. So what you do is you take the this upper bound for the curvature, this constant L, and the analog of this in the quadratic case is lambda max, the biggest eigenvalue of this matrix in the middle of the quadratic form. Next, you take the strong convexity constant, which is this lower bound in the curvature, and its analog is the minimum eigenvalue of the matrix in the quadratic form in the quadratic case. And once you sort of make these two substitutions, so you just take the theorem from the quadratic case. Every instance where lambda max appears, you replace it with L. Every instance where lambda min appears, you replace it with mu, and this is including in the the convergence rate, so the result, and in the choice of the step length, and you end up basically with the same result. Okay, you end up with the exact same story. So this is again the moral of the story here is that yes, quadratic problems are simple, but oftentimes they, at least for first order methods, they're actually very telling. If you can get a first order method that work well in a quadratic problem, then it probably works okay on general problems. There are a few notable exceptions, but generally speaking, this is, quadratic problems are a good test case. Okay, so let's interpret this result a little more, because this is one of the, this result is one of the, when people, quote convergence rate of gradient descent, they're really sort of thinking about, this result. So let's interpret it a little bit more. What does this result sort of mean? Well, what it means is that, so before we always said, and in optimization, it's very common to state result in terms of the convergence rate. So how fast does the optimization error go down? How fast does the suboptimality gap go down? So your function value at current iterate, this difference between the function value at the current iterate and the function value at the optimum. And this gap is always positive because the optimum is the minimum, but how fast does this gap go down? And we've always stated our bounds in terms of, and we saw earlier that these two bounds were, they're sort of related to each other in the sense that one is sort of the square of the other, at least in Euclidean distance. And what we want to do is we want to maybe state the result in a slightly different way, and this is the way of stating it in terms of the complexity of gradient descent. And so, if you sort of you can state the result as how fast these gaps go down, but you can also state it as, okay, what if I prescribe you a tolerance? So let's say a small tolerance called epsilon, okay? And I ask myself, well, how many iterations does it take in order for the algorithm to produce a point that is guaranteed to be within epsilon of either the suboptimality gap or the optimization error? Again, optimization error is the Euclidean distance between the current iterate and the minimizer. And the suboptimality gap is the difference between the function value of the cost value of the current iterate and the cost at the minimum. Okay, so if you sort of take this this type of linear convergence result, and you sort of play a little bit with it, what you see is that, roughly speaking, it takes the order of kappa, again, kappa is the condition number, right, times log 1 over epsilon iterations to get you to to get you a point that is at most the guaranteed within epsilon Euclidean distance of the minimum. Now, this is actually a very nice result for two things. So first is the dependence on epsilon is extremely mild, right? So I can ask for, so you should think about maybe epsilon as like how many digits of accuracy you require, okay? So if epsilon becomes, let's say I want, before I was asking for, 4 digits of accuracy, and now let's say I want 12 digits of accuracy. Right, this seems like a lot more, 10 to the minus 4 to 10 to the minus 12. But basically what you need, because of the very robust nature of gradient descent, the very quick convergence nature of gradient descent, you basically just need to run it for 3 times as long. Okay, so basically running it for twice as long doubles the number of significant digits in your answer. Okay, that's sort of the takeaway, this logarithmic dependence on epsilon. The other thing is you see how the complexity really depends on the curvature, right? The dependence on epsilon is logarithmic, but the dependence on this condition number, which is a measure of the multi-scale nature or the worst case curvature of the problem, is actually linear. So the computational complexity of gradient descent really depends much more on how well behaved, in some sense, the objective function is compared to how accurate of a solution you're asking for it. Okay, that's sort of the takeaway. That's the first takeaway. The other takeaway is that if you look at this bound, dimension doesn't appear, right? This optimization variable x is an RD, but nowhere do you see this quantity d appearing in this bound. Now, one could argue that this d is perhaps hidden away in the choice of kappa, right? Because the more dimensions you have, maybe the curvature of the function, upper and lower bounds, they need to be correspondingly sort of expanded in order to maintain the validity of the bounds. But at the end of the day, there's no direct dependence on the dimension in the convergence rate. And this is something that is quite wondrous about first order methods. And so if you look at a lot of the other methods, if you go back to earlier sort of methods for optimization, you will see that these things like the Ned-Melder, let's say a lot of the methods for zero order optimization, so this is optimization that algorithms that don't use, let's say, the gradient information. They just use the function value information. They will oftentimes have very, very poor dependence on the dimension, almost exponential, sometimes exponential dependence on the dimension. And so what this means is that for large-scale problems where you may have a lot of decision variables, these algorithms are just a no-go because they converge very, very slowly. Gradient descent has this property that it doesn't matter. It converges basically at the same rate, assuming that your condition number, your upper and lower bounds are comparable for problems of different dimension. Gradient descent will converge at basically the same rate. And so this independence of dimension is something very appealing about gradient descent. And we'll see this is not just a property of gradient descent. This is generally a property of first order methods. So just like before, we stated the theorem in terms of how fast the optimization error decreases. You could restate this theorem in terms of the objective value. And it's actually not hard to do this conversion. Maybe I'll leave this as a homework problem for you. Because if you sort of think about geometrically what's going on, right? If I have what the conditions on the strong smoothness and the strong convexity assumptions, what this means is that basically if I look at my this objective function and I let's say I look at it starting away from the origin. So I guess not the origin, the minimizer. It's kind of sandwiched in between two quadratic functions. The first is the quadratic function that has uniform curvature L, so the strong smoothness constant in every direction. So this is in some sense the upper bound, and the other is the lower bound, which is this quadratic function that has uniform curvature mu, the strong convexity constant in every direction. And so this whatever your your function is doing, it's kind of sandwiched in between these two functions. Okay, and once you sort of and so it's perhaps not surprising that the convergence results for quadratic functions translate immediately to, or translate analogously, if you will, just by replacing some of the constants with their counterparts in the general nonlinear case, to sort of just strongly smooth and strongly convex problems. And so if you look at this corollary, basically, if since the function right is sandwiched in between these two quadratics, then the function value right cannot sort of vary more than quadratically away from the iterate distance, so the optimization error. And you really see this here, right? So when I convert the when you can sort of convert the bound on the you can convert the bound on the optimization error into a bound on the the suboptimality gap, which is what is being done in this corollary. Just to remind you, all the proofs are in the references, so make sure you look at those. Those are really sort of the meat of this course. Okay, so let's take a look at these two assumptions, strong convexity and strong smoothness in greater detail. Let's start with strong convexity because this is perhaps closer to the condition of convexity that hopefully some of you guys have seen before. So let's look at the definition first. Actually, these are all equivalent definitions. So I'm just giving you the definition that is most obviously connected to the definition of convexity. So if you look on the right side of this definition of strong convexity, and you remove this quadratic term, this mu over 2 Euclidean distance between x and y squared term, what you're left with is you're just left with the usual first order characterization of convexity, which says that if I take any point of this function, I take the first order Taylor expansion of the function at this point, then the rest of the function uniformly sits above this first order Taylor expansion. And I can take this first order Taylor expansion at any point. Right? This is true for Taylor expansion at any point. Here, what it says is, okay, not only does it have to sit uniformly above, it has to sit uniformly above by a quadratic margin. And the constant in front of this quadratic margin, that's this, mu over 2 x minus y Euclidean distance squared term. And the constant in front of this quadratic margin, this mu, this is the strong convexity constant. Okay? So this is why it's called strong convexity. This is how it relates to the usual definition of convexity. And now let's look at some equivalent characterizations. So I'm going to give you three. So the first one will be a zeroth order characterization, completely in terms of the function value. The second will be a first order characterization, which is in terms of the gradient. And the last one is the second order characterization, which you've already seen in terms of the Hessian. Now, obviously, these characterizations are only equivalent if the function is first and second order differentiable. So let's look at the zeroth order characterization, the one completely in terms of function values. Again, you can relate this to the zeroth order characterization of convexity, which is just Jensen's inequality. So this is, in some sense, a tightening of Jensen's inequality. So what does Jensen's inequality say? If I take a function, right, and I take 2 points on its graph, right, and I connect them by a straight line segment, then the function sits below this line segment, right? That's what Jensen's inequality, graphically is trying to say. So what you say here is that this function must again sit below by a margin. This margin is quadratic, but it also depends in how far away these two original points that you chose to draw the line segment between are. But it also has this dependence on exactly where on this line segment you are, because the line segment obviously has to touch the. It can't always be quadratic. It has to touch the points at each of the original function at each of the endpoints. And so this is the alpha times 1 minus alpha term. But basically what it says is that not only does it have to sit below the actual graph, the function has to sit below the line segment, it has to sit below the line segment by some margin. Okay, so again, it's a strengthening of the usual convexity assumption. Okay, this is the zeroth order characterization. The first order characterization is in terms of monotonicity of the gradient. And so this is perhaps a slightly foreign concept to you guys, but this is a multivariate generalization of the notion of monotonicity, and it's actually a very useful notion. This notion doesn't really appear in statistics. It's kind of odd, but it's making a kind of a comeback through all this optimal transport stuff. But it's in some sense the correct generalization of convexity to higher dimensions. And so if you recall why monotonicity comes in, is that if I have let's say you have a function, okay, in 1D, so the function is from R to R. If it's convex, what it really means is that if I look at its gradient, right, this gradient is monotonically increasing. Right? Now, there's a generalization of this to higher dimensions. So you can say a convex, multivariate convex function, its gradient has to be monotone. You just have to define monotonicity correctly. And what is the definition of monotonicity? Well, if you look on this statement of strong monotonicity, you just replace this quadratic thing on the right side with 0. That's the definition of monotonicity. Okay, and so now if I go back, if I reduce to keep things simple back to the scalar case, so now the gradient is just a scalar, right? What it says is that the gradient of this convex function f at x minus the difference between the gradient of between 2 points x and y, right, multiplied by the difference between the points itself, x and y. So the difference between the gradients of x and y times the difference between the points itself, x and y. This product has to be non-negative. That's what it means to be convex in the scalar case. And this is just a generalization of this to the multivariable case, where you replace this product with the inner product over vectors. Okay. Okay, so that's monotonicity. So what's strong monotonicity? Well, again, what you do is you have to strengthen this. Instead of just being bigger than or equal to 0, right, it has to be bigger than or equal to a quadratic term that depends on the distance between x and y. Okay, so this is strong monotonicity. And the last one you've seen before. The last one is just, it corresponds to a strong curvature of the Hessian, right? So if the Hessian is always, the function always curves upward, so the Hessian is non-negative. More generally, the Hessian is positive semi-definite, then this function is convex. Now, it has to curve upward sufficiently, and so it has to be sufficiently strongly convex, so the Hessian has to be sufficiently positive definite. And this is the second order characterization that we've already seen. Okay, so those were all the equivalent characterizations of strong convexity. Let's move on to the strong smoothness assumption. This might be perhaps a slightly more foreign assumption to you guys, but as we'll see, it's actually quite natural. So what does it mean for a function to be strongly smooth? Well, what it means is that if you recall the strong convexity assumption, right, what it says is that the function always sits below basically it says that the function is always emits a quadratic lower bound, right? Always sits above this first order Taylor expansion plus this quadratic term, right? So strong smoothness is in some sense the complementary assumption. What it says is that this function always emits a quadratic upper bound, right? So this function always sits below the first order Taylor expansion plus a quadratic term, okay? And the constant in front of this quadratic term, that is the strong smoothness constant, okay? And this, again, has to be true for any points x and y. Okay, so just like in the strong convexity case. Now, the fact that this strong smoothness condition really complements the strong convexity condition, you see it in all the other characterizations as well. So what I'm going to give you is I'm going to give you zeroth, first, and second order characterizations. Okay, so let's start with the zeroth order characterization. What you see is it's in some sense a reverse of the characterization of strong convexity. So remember, in strong convexity, right, in the zeroth order characterization, what it says is that there needs to be a gap between the line segment and the actual graph of the function. So if I take the function, I pick 2 points in this graph, I connect it to a line segment, it says that the graph of the function sits, there needs to be some non-zero gap between between the line segment and the graph of the function, except at the endpoints, right? And so what this, in strong smoothness, what you see is that this relationship is reversed. It says that yes, there needs to be this gap, but this gap itself cannot be too big. Okay, and this amount by which it cannot be too big is again quadratic. Okay, so basically from a like a pattern matching point, what you did was you reversed the inequality, right, in the zeroth order characterization of strong convexity, and you replace the quadratic term with this quadratic term. Instead of depending on mu, it depends on L, which is the strong smoothness constant here. Okay. The next concept is something called cocoercivity. We will look more at this concept later when we talk about first order methods in greater generality. But again, it's kind of this is a slightly sort of strange characterization, because what it says is that you need this gradient to be it's not sort of it's not monotone, because the right side does not depend on the distance between x and y, but it is lower bounded away from 0. But this lower bound now depends on the value of the gradient instead of the value of the points. Okay, that's what co-coercivity means. We'll talk more about this in a future lecture. The next first order characterization is perhaps the one that's most familiar to you guys. What it basically means that the gradient is Lipschitz continuous, okay, with respect to the Euclidean distance. Okay, this is probably the most common characterization of strong smoothness, but the most useful one again is this, quadratic upper bound for the function. Okay, and the last one you've already seen. This is the second order characterization. What it means is that there's an upper bound in the curvature of the Hessian. Okay, and this really makes quite a bit of sense, right? If you think back to the definition on the previous slide, right? What it says is that it admits this quadratic upper bound, where the quadratic term has a coefficient that's bounded by the strong smoothness constant L, right? So what it really means is that the curvature cannot go up any faster than L, and so again you see it here directly in the second order characterization in terms of the Hessian. Okay, so that was the assumptions that we use in the study of gradient descent. So now let's look at maybe a more practical variant of gradient descent. You notice that in all the theorems that we proved before, we've actually only talked about two ways of setting the step length. One is the exact line search, and the other one is a constant step size, but this constant depends on certain parameters that usually you don't know in practice. Neither of these strategies are really that ideal, and so what we're going to look at right now is a very practical way of determining the step length. And it's actually not a particular choice by an algorithm. And this algorithm is called a line search, or more concretely, a backtracking line search. Okay, so the idea for backtracking line search is actually very simple. So first, you have to determine what is a criteria for a good step length. Okay, and in a backtracking line search, there are sort of a few different criteria that you can use, but the most common one is what's called a sufficient descent condition. And what this says is that you have to achieve a certain fraction of the predicted decrease in the objective function. Now, let's unpack what that means. So when I take a first order approximation to the objective function around the current iterate, this just means by first order approximation, I just mean the gradient-based approximation. This gradient-based approximation will predict that the objective function will change by a certain amount as I move within the vicinity of the current iterate. And this prediction of how much the objective function will change, this is basically my predicted decrease. Now, what I want is when I pick a particular step size, so I make a particular move to another, my next, candidate iterate, let's say, I want the difference in the function values between this candidate iterate and the current iterate to be not too small. I want it to be at least, let's say, half or maybe 10% of the decrease predicted by the first order model at the current iterate. Okay, and that's basically what the sufficient descent condition, intuitively is trying to capture. So on the left side, you have the difference between the candidate next point, right, and the current iterate, and on the right side, you have the predicted difference between the function value at the candidate point and at the current iterate, according to this first order gradient model. This parameter alpha, right? This parameter alpha is the is this sort of fraction that controls how much of a predicted decrease you're willing to accept. So a small alpha means you're willing to accept a very small fraction of the predicted decrease. A big alpha is more stringent. You're only willing to accept quite large fraction of the predicted decrease. So a big alpha will generally force you to take smaller step sizes. A small alpha will allow you to get away with bigger step sizes. But the decrease in objective value might be comparable. Okay, so there's a typo on this slide. So the eta t in the first line of the equation, that should be an eta. But this is, again, just a sufficient descent condition, and this is the criteria for accepting a step length. Okay, so any step length that satisfies the sufficient descent condition, we're going to declare it's good, and we're going to be accepting. Okay, so with that in mind, with what we want out of the line search in mind, let's just let's go over the backtracking algorithm. The algorithm is actually very simple. What you do is you start with some step size, usually the unit step size, so eta is 1, and then what you do is you just decrease the step size by a small constant. It could be a half, could be 0.9, and then you just check whether it satisfies this step length satisfies the sufficient descent condition. If it doesn't, you decrease again by the same small constant, and you just repeat until eventually you find a point that satisfies the sufficient descent condition. Now, I want you to maybe I'll leave this as a homework problem of if the objective function is smooth, you will always find such a point, and so maybe I'll leave this as a homework problem. But remember at the very beginning of the video, I alluded to the fact that gradient descent is one of the most robust algorithms out there, in the sense that if you set the step length, below some threshold, the algorithm will work. Well, this backtracking line search is sort of motivated by this. As long as you pick step lengths that are smaller than some threshold, that's why you constantly walk back the candidate step size. The idea is that eventually you're going to get it below this threshold, and then everything is going to work. I guess I should comment on this since we're on the topic of step length. Was that so? If you look at all the convergence results for gradient descent, including the ones that we've proven before, they're all for specific choices of step lengths, right? And this is a thing, because how fast you converge really depends on how big of step sizes you take. What I mean by gradient descent will work with as long as the step length is not too big is that if the step length is not too big, right, below some threshold, you will get linear convergence. Now, the exact convergence rate, so that the factor with which you're reducing the optimization error, the factor by which you're reducing the suboptimality gap at each iteration, this is going to depend on your step size, yes. But this number is just going to be some number that's smaller than 1, right? The exact value will depend on the step size, but the fact that it's smaller than 1 will not. Okay, as long as the step size is smaller than some threshold. And so as long as you have your step length smaller than some threshold, you'll get a sequence of iterates that converges linearly. They may not all converge at the same rate. The rate, again, will depend on the step size, but you will get this linear convergence, which at the end of the day, it doesn't matter too much, because if you recall the sample complexity of gradient descent, right, how the convergence, this constant by which you converge appear, right? This constant depends on the condition number, and so essentially what you can think about is that what you're essentially doing is you're futzing this, this constant in front of this sample complexity by choosing different step lengths. And so maybe you choose a step length that it might take twice as many iterations to converge, but again, it's still a linear convergence rate. Okay, so let's look at the convergence of gradient descent with a backtracking line search. We saw earlier that even with an exact line search, it's not like the performance really deviates that much from the usual linear rate of convergence that we expect. And you really see it here. So again, you still have a linear convergence rate, stated in this case in terms of the function value. But you don't see a... so you see the dependence of the this constant in front of the convergence rate on the step length. In here, it's not directly in terms of the step length, it's in terms of the parameters of the line search, but that's really how the dependence on the parameters of the line search sort of arises. It's because it's going to, first it's going to depend through the step length, and ultimately then on the parameters of the line search. So what's interesting about this convergence rate is that there are sort of two terms, okay? The first term is in some sense let's take a step back. So when you study this type of convergence in terms of a line search, what you first oftentimes prove is that there exists a step size that will satisfy the sufficient descent condition. Okay, and the way that these proofs go, again, it's by sort of bounding Taylor expansion error. What end up happening is that you will get actually a threshold such that any any step size below this threshold will satisfy the sufficient descent condition. Again, if the sufficient descent condition is of the general form that we saw earlier. And so what this means is that if I'm backtracking, right, then there's no way that I'm going to, again, each time when I backtrack, I reduce the step size by a factor of beta, right? So if my threshold, let's call it tau, then the step length that I take will always be at least beta times tau, right? Because each time you only reduce the step length by a factor beta, and you know that every time, as long as once you sort of hit this threshold, right, any step length smaller will be accepted. And so the smallest possible step length is you start out just slightly above the threshold, right? Maybe it's not accepted, and then you multiply by beta, and now you are within this you're smaller than the threshold, and so your step length is going to be accepted. And so this is usually, you can think about it as this type of proofs of convergence for backtracking line search as just carrying out the analysis for a fixed step length, but the fixed step length is this beta tau value, okay? And so I actually am not, so all the other results that I've showed you in this video, proofs are again in the references, but this is a result that I'm just going to refer you to, you know, Boyd and Vandenberg. Boyd and Vandenberg, it's standard textbook on convex optimization. It doesn't really talk about algorithms that much, but gradient descent is a, you know, is a basic or fundamental enough algorithm that they have analysis of it in their book. And so check it out in there. Okay, so thus far, right, what we've talked about is basically the convergence. These are sort of very classical results about gradient descent. So convergence on quadratic functions, convergence in on strongly convex and strongly smooth functions. And so now we're going to move into perhaps some of the more modern analysis of gradient descent, in particular trying to relax the convexity assumption and also trying to look at how it does on, you know, non-convex problems. So essentially, what we're going to do is we're going to do this slowly. And what we're going to do is we're going to relax the convexity condition bit by bit, okay? So instead of assuming strong convexity, what we're going to do is we're going to assume some other type of conditions. And we're going to look at two in particular. And one is, you know, the first one, I guess I'll just call it regularity condition. It's, you'll see sort of, it's not like a real condition, but it will motivate some of the later condition, which is this Polyak Logis width condition, this PL condition. Okay, so why first do we care about this type of analysis? I'm actually kind of torn about this. I was not entirely sure I was going to include this bit in the video. And the reason is, as a statistician, you almost always have strong convexity, because for almost all practical problems, when you try and solve them, you are going to, you know, do some type of L2 regularization, let's say. I mean, this is very common. And so whenever you add L2 regularization, you immediately have strong convexity. And so all this, you know, analysis of gradient descent with, you know, relaxed version of strong convexity, they're not really that important. The second thing is, even if your objective function, you know, doesn't have strong convexity, you can always add a little bit in just by you know, putting in a little bit of regularization. Now, how much you put in, right? Maybe it depends on you know, how many samples you have, because at the end of the day, when you, let's say, solve your statistical estimation problem, let's say this optimization problem, you are the actual optimum of this optimization problem is itself an estimate of some population quantity. So for example, think about your MLE, right? The actual minimizer is the maximum likelihood estimator, and this is an estimate of the population parameter. And so based on your sample size, you expect there's, you know, a certain amount of deviation between your estimator value and the sample and the population parameter value. And so what you can do is you can just add a small amount of L2 regularization. Adding L2 regularization, of course, perturbs the solution, perturbs the estimator a little bit. But as long as you don't perturb it by more than the estimation error, more than the statistical error, it sort of doesn't matter in the grand scheme of things. And so you can always add, even if you come up with a problem that doesn't have L2 regularization, if it's statistical in nature, so meaning that you are looking at the optimum as itself an estimator of something else, then you can always add a little bit of L2 regularization to make the problem strongly convex. And then all the analysis that sort of we saw before would apply. And so I was, you know, kind of debating on whether I should include this, because perhaps you could argue that it's not really relevant to statistical practice. But nevertheless, I think it's good to see some of these conditions, because at the end of the day, a lot of the, you know, the techniques that arise in optimization is ultimately, you know, also very useful for statistical problems. So for example, you know, the study of the MLE, you know, proving convergence rate, a lot of it is using ideas of strong convexity, which is something that ultimately, you know, first came from optimization. And so maybe when you see some of these conditions, you'll find it useful. But anyway, so here's an example of a problem that doesn't satisfy strong convexity. It's just logit state regression. The reason why it doesn't satisfy strong convexity is because you can look at the form of the Hessian, right? And if I take x to be if I take x to be huge, right, then you see that these coefficients in front of each term in the sum that comprise the Hessian is going to be very small. And so basically what it's saying is that very far away from the origin, this objective function, this logistic regression objective function, has very little curvature. And so it's going to violate the strong convexity condition at those points. Now, one could argue whether this is actually relevant because you certainly don't expect the logistic regression coefficient to be sort of all the way out there in these regions of the parameter space where there's no sort of strong convexity. But nevertheless, the complaint still stands. This is if you want to be technical or formal about it, this is a problem where you don't have strong convexity, so the analysis that you saw before doesn't immediately apply. Okay, so let's move on to the first condition, which is what we're going to call a regularity condition. And this condition you see is a little bit silly. Essentially, what it does is you sort of write the proof of gradient descent, and then you look at there's an important step. You can inspect the proof in the references. It's a very short proof, and the reason why it's very short is because what you're going to do is you're going to write the proof, and then at some point you're going to arrive at an inequality, or you're going to arrive at some an expression that you want to bound. Okay, and the regularity condition basically just directly assumes you can bound this. Okay, and if you look at the form of the regularity condition, and the reason why we actually use it, not just this is not like entirely cheating, is that the form of the regularity condition is somewhat reasonable. Okay, so if you recall from back in the day, not back in the day, but if you recall from before, we had these two conditions of strong convexity and strong smoothness, right? And there are two sort of equivalent characterizations of them. So, well, there are equivalent characterizations of them. One of the equivalent characterizations of strong convexity was strong monotonicity of the gradient, right? And one of the equivalent characterizations of strong smoothness was co-coercivity of the gradient. And so if you look at this regularity condition, it's basically some combination of the two, okay? You recall the quantity on the left, right? This inner product between the difference of gradients and the difference between the points themselves. This is the quantity that you're going to look to ascertain whether a function is monotone or not. And what you have here is you have a quantitative version of monotonicity, where the right side is a combination, this lower bound on this inner product between the difference between the gradient and the points at which the gradients are taken, is a sum between the lower bound from the strong convexity, lower bound from strong monotonicity, which is an equivalent characterization of strong convexity, and the lower bound from co-coercivity, which is an equivalent characterization of strong smoothness. So in some sense, it's like strong convexity plus strong smoothness lumped in here together as one. Okay, and so you might say, okay, now this is actually stronger than the strong convexity condition, because after all, if it satisfies this regularity condition, for sure this thing is strongly convex, right? Because you've made that sort of lower bound even stronger. The key is that you're only going to recall before strong convexity and strong smoothness, you have to sort of apply this globally, right? The key here is that you only apply this to pairs x and x star. So x can vary. So one of the arguments can vary, it's over all points, but the other argument is always the minimizer, always the optimum. Okay, and so this is the way in which it's weaker than the strong smoothness and strong convexity assumptions, which has to be true for all x and y. Here I'm just fixing y to be x star. Okay. Okay, so let's look at the convergence of gradient descent on objective functions that satisfy the preceding regularity condition. And no surprises here, the convergence is again linear, and it is very similar to the results that we've seen before. The only difference is that the factor, sort of the rate, the contraction factor in the linear convergence rate is slightly different this time. We've stated the rates in terms of the constants that appear in the regularity condition, but if you take these constants as analogs of the strong convexity and strong smoothness constants, then this is basically 1 minus 1 over the condition number. And so the convergence rate is really very similar to before. Okay, the second condition that we're going to look at is called the PL condition. Now, this condition is, first, it's a condition that is quite common in the literature. That's why we present it here. But it's a condition that is a bit strange. So let me unpack it for you. What it says is there is a constant, and this constant is in some sense analog to the strong convexity constant, that lower bounds the squared of the magnitude of the gradient in the Euclidean norm by the suboptimality of the function. Okay, so what this says is that the only points at which the gradient are 0 are the global minima. Okay, so basically there are no points in which the gradient is 0, but you're still not at the global minimum function value. Now there can be multiple global minima, right? It doesn't have to be unique, but it just implies that if you're far away from, if your objective function is big, the suboptimality gap is big, then the gradient is also big, meaning that intuitively you can make progress if your suboptimality gap is big. So what is actually very dangerous for an optimization algorithm is if your objective function has like some flat region, and this flat region is actually not the minimum. Because if I have a first order optimization algorithm and all it does is uses this local information to sort of decide where to go next, if you have a flat region, because it only sees the neighborhood, this neighborhood's all flat, then once you end up in here, it effectively you can't get out. If you recall the step lengths, sort of how this these line search algorithm moves, certainly gradient descent, is you move along the search direction. Well, in this case, your search direction is the gradient. If the function is very flat, the gradient is very small. So each time you're only going to take very small steps. So your algorithm, your iterates, might get stuck in this flat region. And this PL condition basically says that this cannot happen. If I'm not at the local minimum, the gradient is always large in magnitude, meaning you can make progress. Okay. So let's look at the convergence of gradient descent on objective functions that are strongly smooth and that satisfy the PL condition. So basically, this PL condition kind of replaces the strong convexity condition. So here, what you do is you again take a constant step size. The step size here is 1 over the strong smoothness constant. And if you take the step size, then gradient descent will converge again at this linear rate. This linear rate is very similar to the linear rate we've seen before. The contraction constant is 1 minus 1 over the condition number. In this case, the result is stated in terms of convergence of the function values. Again, I want to emphasize that the PL condition doesn't imply that the global minimizer is unique. And the proof, again, is in the references, so I encourage you guys to read that. But one thing I want you to take away from the proof is that it contains this tidbit that's perhaps not exactly obvious, so I want to point it out to you. But the way that this is proved is to interpret gradient descent as what is called a majorization minimization method. So this is oftentimes we abbreviate it as this MM method. This is a standard sort of approach to optimization. In statistics, the most well-known example of this is the EM algorithm. So maybe you guys have seen this in your applied stats course, your methodology course. But the EM algorithm is probably the most well-known instance of a majorization minimization method. We'll see exactly what this is on the next slide. But the proof of the convergence of gradient descent under the PL condition actually comes by interpreting gradient descent with this fixed step size on functions that satisfy these conditions as a majorization minimization method. Okay, so why is gradient descent a majorization minimization method? So first, it is actually not hard to check that the gradient descent step, you can write it as a argmin of a surrogate to the objective function. And what is this surrogate? What you do is you take the first order Taylor expansion, right? Now, this is a linear function, so you can't talk about minimizing this linear function, especially if the region is unconstrained. For constraint problems, there are algorithms that minimize directly the linear surrogate. These are like Frank-Wolf type methods. But for unconstrained problems, you cannot minimize the linear surrogate because the minimum is minus infinity. And so what you do is you regularize a little bit by adding this quadratic term, this 1 over 2 over eta t times the distance, the square distance between x and the current iterate. Okay. Now, you can imagine what this term does. So if eta is very small, because eta appears in the denominator, this quadratic term would be very large. Okay, and so basically when you move away from the current iterate, this quadratic term will get very big very quickly. And so what this small eta t does is that, eta t, again, remember, is a step length parameter. What a small eta t does is it prevents the new iterate, x sub t plus 1, from being far away from xt. Again, this is how you get a small step length. And vice versa, right? If eta t is very big, then this quadratic term is actually, quite small, and so it takes a while before this quadratic term starts to dominate the linear term, and therefore you can, move further away. X sub t plus 1 will be quite far away from xt. Okay. So this is the interpretation of gradient descent. You can just check that, if you write down the optimality condition of this quadratic minimization problem, which you can do in closed form because it's just a quadratic, you'll see that the optimality condition is directly equivalent to the gradient descent update rule. Okay, so let's call this quadratic surrogate f tilde, okay? And we need to make a couple observations about f tilde. First, f tilde agrees with f in the sense of the function value agreeing at xt. Okay. We index f tilde by the iterate because you're going to construct a different surrogate at each iterate, because again, it's the Taylor expansion at the current iterate. And you also might pick a different step length per iterate. The other thing to note is that, again, assuming f is strongly smooth, right? Then if I pick this eta t small enough, then by the quadratic upper bound from the strong smoothness condition, I know that if I pick eta t small enough, then this surrogate, this f tilde sub t, right, will be bigger than the quadratic upper bound. And so what this means is that f tilde sub t is going to majorize f, in the sense that f is always going to sit under f tilde sub t if I pick eta t to be small enough. And exactly how small? Well, it needs to be smaller than 1 over the Lipschitz constant, right? Because this type of quadratic upper bound is this, this functions of the form of f tilde t. This is exactly the thing that appears in the quadratic upper bound from the strong smoothness condition. Right? Okay. So with these two things in mind, you can immediately see that gradient descent is a descent method. So first, you know that f of xt plus 1, so the function value at next iterate, is less than or equal to f tilde at xt plus 1, because f tilde at xt plus 1 is a, it majorizes f, right? So it's the graph of f sits below the graph of f tilde t, okay? Now, you know that xt plus 1 minimizes f tilde t, so that's how you get the second inequality, right? And finally, by the property that the surrogate is sharp, is tight at xt, right? You get the last equality. And so you chain these two inequalities together to get that f of xt plus 1 is always smaller than f of xt. And so gradient descent is a descent method. And why it's a descent method is because it has this majorization minimization property. You'll see this sort of this type of argument again in analysis of EM algorithm. Here the f tilde t is done by instead of using the strong smoothness quadratic upper bound, what you use a Jensen's inequality, exchanging integration and expectation to basically get an upper bound. But here, what we're just using the strong smoothness property. Okay, so the proof actually is basically a quantitative version. So instead of just saying that f of xt plus 1 is smaller than f of xt, for a fixed step length, you can actually show that you can actually get a quantitative bound in its decrease. And that's how kind of the proof goes. Okay, so last but not least, I want to perhaps give you an application of the PL condition. I mean, why is this condition more useful than, let's say, the strong convexity condition? And one classic example application is we can again go back to a quadratic, and this is the case of the quadratic where you don't have the matrix in the middle being positive definite. It's actually positive semi-definite. So there are some directions in which the quadratic function, the objective function, is flat. Okay. And so this is not a strongly convex function, because along these directions in which the objective function is flat, you don't have strong convexity, right? The objective function doesn't curve upward. And so you would expect that if you just knew about, let's say, gradient descent converges linearly under strong smoothness and strong convexity, then you might think that gradient descent does not converge linearly here, when in fact it does. And the way to see it is to use this PL condition. Okay, so what is overparameterized least squares? Hopefully you guys have all seen this before. The idea is you're solving a least squares problem where the number of parameters exceeds the number of samples. Okay, this is very typical setting these days with high dimensional statistics. But we're not worried about the statistical properties of this. We're purely worried about the computational aspects that arise when you try to compute such an estimator. Okay, and again, it's overparameterized. Therefore, the Hessian, which is this XX transpose matrix, this grand matrix, is rank deficient. Okay, here. Here we're using an optimization notation. So the features are denoted by A, and the responses are denoted by B. The optimization variable is X. It's slightly confusing, but this is the standard notation in optimization. And this regime has various applications. In particular, it shows up in a lot of theoretical models for deep neural networks. Okay, so here we're going to look at the convergence of gradient descent on this overparameterized least squares problems. And essentially, the idea is that this overparameterized least square objective function actually satisfies the PL condition. And therefore, gradient descent achieves the linear rate of convergence. So none of that is very surprising. What I want you to point out is that if you look at the contraction factor in the linear convergence rate, it's, again, 1 minus 1 over the condition number, except the condition number here is defined in terms of the smallest non-zero singular value of A. More precisely, it's 1 over the square of the, it's the square of the largest singular value of A divided by the square of the smallest non-zero singular value of A. Okay. And so in some sense, all the zero singular values, the null space of A, the directions in which the objective has no curvature, in some sense, it doesn't matter. And there is actually a very intuitive explanation for this. Maybe I'll have you guys explore this in the homework. It's that gradient descent in this case really only operates in the subspace in which there is curvature in the objective function. So it's not super hard to see this just by looking at the gradient, because you notice that if I have this objective function, the gradient actually is always in the range of A, right? So if the gradient is always in the range of A, then in some sense it's orthogonal to, the gradient is always going to be in the range of A transpose. So it's in some sense always going to be orthogonal to the null space of A. And this is why you don't have any dependence on the curvature of the objective function inside this null space of A, because the gradient descent iteration in some sense never hits it. In the machine learning literature, what you will see is that this is known as what's called the implicit bias of gradient descent. It's an instance of this implicit bias, and one of the properties of this is that if you initialize it, so gradient descent basically never moves in the null space. So whatever component of the solution, in the null space that you initialize, whatever component of whatever point you initialize it, this point has some component in this null space, and this component will just forever stay the same. And so depending on where you initialize, you're going to get to a different optimal solution. Again, because there's no curvature, there's non-unique minimizers here. Depending on where you initialize, you're going to end up at a different optimal solution, optimal point. And if you initialize at the origin, then basically you're going to get to the point where there's no component in the null space. And this is what's called the minimum norm solution, right? Also it's what the pseudo inverse would give you if you try to solve this over parameterized least squares problem with the pseudo inverse. Okay, so that's a statistical connection for you. Okay, so last but not least, let's talk about non-convex optimization. This is an active area of research, so I won't talk about this too much, but again, if you're curious, come talk to me in office hours, and I'm happy to give you guys references. Okay, so if you take a class like IRE 611, or whatever that class number is, it's a class out of Stephen Boyd's book, you might come to the impression that almost all problems can be made convex. That is not true. There are many, many problems that are non-convex, and here is just a smattering of examples. Matrix completion, a lot of matrix factorization problems. They're what's called biconvex in the sense that there's two blocks of variables, right? These are the two factors of the matrix that you're trying to factorize. And if I fix one of the blocks, then it's convex in the other block. But jointly, they're not convex. These problems are called biconvex. Dictionary learning is a very similar one. It's an instance of this matrix factorization problem, except now you have some extra sparsity constraints on one of the factors which you're going to interpret as sort of the coefficients of the original data points in terms of the dictionaries that you learn. Fitting mixture models, so Gaussian mixture models, or any type of mixture models. The maximum likelihood estimator is generally non-convex. The training neural networks, right, definitely non-convex, except for maybe the simplest case. So when you now move into non-convex problems, you have to temper your expectations a little bit. So I know that, in this past lecture, we've seen sort of, gradient descent convergence result after convergence result that, say, oh, it converges linearly. This is, by the way, a very, very fast rate of convergence. If you think about, this rate of convergence compared to statistical rates of convergence, which are oftentimes, very, very sublinear, right? It's like 1 over root n versus, in this case, it's like, e to the n, basically. It's a very, very fast rate of convergence. And so, you have to temper your expectations in a non-convex regime a little bit. And so first, if your problem is not convex without additional structural assumptions, you cannot really hope to find the global minimum. Because the real issue, the fundamental problem is that these first order methods, they're fundamentally local algorithms, right? They only see the points that they sort of move through. And so this doesn't give them a picture of what the entire objective function looks like. You could say that, oh, maybe I'll try to cover the whole space, but this is where you get into the curse of dimensionality. You can't really do this in a computationally feasible way. And so you have to temper your expectations. So there's not going to be any convergence to global minimum. Okay, so what can you expect? So you can expect global convergence to stationary points. So what I mean by global convergence is this convergence will occur regardless of where you start, where you choose to initialize the algorithm. Remember, all these algorithms, as gradient descent in particular, but most of the algorithms we're talking about require an initial point. Okay. global convergence to local minima, meaning, again, regardless of where you start, you will get to a local min. Okay? And finally, you can talk about local convergence to global minimum, meaning that if I start in the vicinity of a global minimum, I will get to the global minimum. So in this class, we're going to focus on the first two. The latter one is actually not really that different from a lot of the convergence analysis that we've sort of seen before. What you do is you kind of restrict yourself to a neighborhood of the local minimum, and as long as this objective function locally in this neighborhood is strongly convex and strongly smooth, you will kind of get the same type of convergence behavior as you saw before in the convex case, as long as you initialize within this neighborhood. The reason is, if you think about a lot of the convergence results that we've seen, right, what it says is that, at least in terms of the Euclidean norm, you're always sort of reducing the optimization error. You're always reducing the distance to the optimum at each iteration. So that means if I start within this neighborhood that has nice properties, I'm going to stay within this neighborhood of the optimum. And so you can just borrow a lot of the analysis wholesale for this setup. And so we're not going to worry too much about local convergence to global minimum. We're going to focus on the first two properties. Okay, so before we get into present the theoretical results, again, proofs are in the references, so definitely go read them there. What do we mean by stationary point? So a stationary point, I'm sure a lot of you guys know, it's also known as a critical point. It's just the point where the gradient is zero. Okay, we'll get asking for convergence to an actual stationary point might be hard, so we're going to relax it to say what is an epsilon stationary point? Well, it's just the point where the norm of the gradient in the Euclidean norm is less than epsilon. Okay. And we're going to use this as a measure of sort of progress. So if you think about before, right, when you talk about convergence, well, you always talk about convergence by, you have some measure of progress. So the two measures that we saw before were the suboptimality gap, right, and the optimization error, which is the distance in the Euclidean norm of the current iterate to the optimum. So here, what we're going to use the norm of the gradient as this metric of how close we are getting to a stationary point. Okay. So gradient descent actually does find stationary points, but this result is slightly different from all the results that we've seen. All the results that we've seen concerns gradient descent generates the sequence of iterates, and all the results that we've seen concern the very last iterate in the sequence, because its gradient descent is always very good at reducing the optimization error and the suboptimality gap, at least on convex problems. But if you want to converge to a stationary point, is instead of using the suboptimality gap, instead of using the optimization error, you're going to use this how close you are to a stationary point, what is the norm of the gradient, then gradient descent is actually not that great at doing this. And so what the best that you can get is what basically is that in this entire sequence of iterates that you've generated, there is going to be one point that is an epsilon stationary point, okay? And the guarantee on the norm of the gradient of this one point, okay, is actually a very weak guarantee. This is a sublinear rate. So instead of the exponential rate, right, some constant to the t, right, what you get is you get a 1 over t rate, polynomial rate. Okay, this is much slower than the linear rate. But again, we don't have any structure on the problem. You don't have convexity. You do have strong smoothness, and you do use the constant step size. And so, but here you just really you can't hope for too much more without strong convexity. Basically, the high level idea is if you want to get linear rates for a gradient descent, you need some version of strong convexity. Maybe not in maybe in terms of the PL condition, in terms of regularity condition, but you need something that guarantees you curvature away from the optimum. If you don't have that, then gradient descent generally only gets this 1 over t rate. You can actually study the convergence of gradient descent for strongly smooth but convex functions in the absence of strong convexity, and you will see that you get a very similar 1 over t rate for the optimization error and the suboptimality gap. Okay. So the other thing, the other thing I want to know is that this does not imply gradient descent converges to a stationary point. It says that along this whole sequence of iterates, there's one point that is an epsilon stationary point. Doesn't mean it's going to be the last point. Okay. So just to hammer home, how much slower this rate is, we can sort of turn this problem on its head and look at how many iterations of gradient descent do you need to guarantee that you find an epsilon stationary point within this entire sequence of iterates. So the analog to this question before is, let's say, how many iterations for gradient descent do you need to find a one over epsilon suboptimal point? Sorry, an epsilon suboptimal point, or a point that's within epsilon of the optimal solution x star. And here, what you see is that instead of the dependence of epsilon being log of 1 over epsilon, you get there isn't this log term anymore. It's just straight up 1 over epsilon. Okay, and it's actually a very slow rate. It's 1 over epsilon squared. So it's really quite a difference from before. Okay. Okay, so we saw before that gradient descent converges to stationary points, but there are several types of stationary points. In particular, there's local min, local max, and what's called a saddle point. And so gradient descent never gets to a local max, so it's always going downhill, right? But it might get to a saddle point, and it might get to a local min. Well, it turns out that gradient descent doesn't almost never gets stuck at saddle point. It might get stuck in very rare circumstances. Like maybe if you started the algorithm at the saddle point, then yeah, it will get stuck there because the gradient is zero, so it just never moves away from the saddle point. But if you just initialize randomly, it almost always gets you to a local min. And the reason is, if you think about the saddle point, it's kind of unstable. You have to, if you get close, but you're not directly on top of the saddle point, then there's going to be some direction of negative curvature, and the gradient is sort of going to try and follow that. And so unless you sort of directly land on the saddle point, it's almost impossible for the gradient descent to get stuck on the saddle point. And so here's just a concrete result to this effect. So I'm going to set up a non-convex quadratic optimization problem. So in particular, this quadratic optimization point, this matrix in the middle of the quadratic form has negative eigenvalues. Okay, so this is an optimization problem that you wouldn't really solve. It's unbounded below, but we're just using this to make the point that it doesn't get stuck in saddle points. And so this sort of optimization is sort of set up so that the origin is the saddle point. Okay, and so if the sequence converges to the origin, then it's gotten stuck in a saddle point. And so again, if you initialize gradient descent at the saddle point, it will never leave. So that's one way you can get stuck. But it turns out that if you draw, let's say, the initial point randomly from, let's say, a Gaussian, and you use a constant step size, then the iterates will, in this case, it will diverge, but it will never get stuck in the saddle point. So this is just a concrete result to this effect of gradient descent never gets stuck in saddle points.